So the first topic we'll discuss is two-photon absorption. Okay, so in the last class we saw how chi3 gives rise to an intensity-dependent refractive index, right? But to be more specific, that was the real part of chi3. And we saw in the beginning how susceptibilities in general are complex numbers, right? So if there is an imaginary part also, then you'll see that it gives rise to what is called two-photon absorption. Okay. So again, let's say you have some material and we have some wave at frequency omega propagating through this material which has some chi3, but now in general this is a complex number, so we'll include the full or we'll assume it as a complex number with both real and imaginary parts. Okay. So the total polarization induced at the frequency omega, right, is sum of two parts. You've seen this many times before, right? One is the linear part and one is the nonlinear or third order part. Right? So we just have one wave of frequency omega and we want to see basically what effect the medium has, the nonlinearity of the medium has on this wave at frequency omega. So we are looking at the polarization at omega only. Right? So again, you can just write these terms. We know the linear one goes as epsilon naught chi1 times the electric field of the input wave, right? And the third order, we know at frequency omega, you can write as right. So this is already in the last class, right? So if you want third order polarization at omega, then we can write omega as omega plus omega minus omega, right? So we get one conjugate term and two the usual term, so we get mod e square e, right? And then again we did this last class, so we wrote this as basically some chi effective times the electric field, right? And so chi effective is the linear term plus this third order term times the mod square of the electric field, which is proportional to intensity, right? And again, proceeding like last time, so the square of the refractive index is 1 plus the susceptibility, right? So if I define this as some effective susceptibility, then I can define some effective refractive index as this, right? So maybe I'll write this as this to the power half, right? And then we proceed again, like we did last time. We say that this nonlinear term is much smaller than the linear term, right? So basically, we can take the linear term out common and then write this as that, right? And now we say that this term is very small. So this is the nonlinear term divided by the linear term. So this quantity is much smaller than 1. So we use the Taylor expansion again, right? And we recognize that 1 plus chi1 is the Bell refractive index. or square root of 1 plus chi1 is the bare refractive index, right, or the linear usual refractive index, which we call n0. So this is approximate, right? And then here we do 1 plus half. So 1 plus chi1 we get n0 square in the denominator, and in the numerator we get 3 by 3 body square. Right? So all this is just repeat of last class. Okay. And so last time what we said was, okay, right, this is n0 plus so last class what we did was, okay, assume chi3 as a real number. Then we said, okay, we have the bare refractive index plus something which is proportional to intensity, right? And if chi3 is real, then this is a real number which we called n2, right? And we wrote the total refractive index as n0 plus n2i. But now let's consider chi3 could have an imaginary part also, right? So then the real part of the refractive index will be the real part of that. So that will be n0 plus so the real part of chi3, right? That will give me the real part of n, right? And then I'll, if chi3 is complex, then there is an imaginary part to the refractive index also, which is basically the imaginary part of this. Okay, so the bare, so let's assume for now that the bare refractive index n0 is real. So we are working, let's say, below the band gap or something, right? So there is no direct absorption. So n0, the linear or the linear refractive index doesn't have an imaginary part, so it's just a real number, right? So we have this imaginary part of the refractive index now, again, which is proportional to intensity, right? And if you again recall your basic electromagnetism, then this imaginary part of the refractive index will give me an absorption, right? Because so we write the propagation of the wave as e to the I k n or k naught n z, right? And this is the refractive index. So if this has a real and imaginary part, you can see that the imaginary part will give me something which goes as e to the minus alpha z, right? So that gives me absorption. So the absorption coefficient, I can define an absorption coefficient alpha effective, right? So here the absorption coefficient, so the usual case in the linear case is defined as 2 omega over c times the imaginary part of the linear refractive index. So if the linear refractive index has a linear imaginary part, then that gives me absorption, right? Similarly, in this nonlinear case, we can define an effective absorption coefficient alpha effective as again 2 omega over c times imaginary part of n here now, right? But now the n is the nonlinear refractive index. So this I can write as so we get 3 omega over c right? And again, usually we want to express this in terms of intensity. So if I write this as some coefficient beta times intensity, or usually it's referred to beta with subscript PPA, denoting 2-photon absorption. right? So I just use the relation of I is equal to again 2n c epsilon naught mod e square. Then from there you can see right. So from here we'll get the two-photon absorption coefficient. Okay, so this two-photon absorption coefficient beta is proportional to the imaginary part of chi. Okay? So if chi3 is real, or if you're working again in the Kleinman symmetry limit far off resonance, then typically we neglect the imaginary part, and then this coefficient is 0, so we don't have any two-photon absorption. But in general, once you get close enough to the band gap or some resonance, then chi3 will have non-negligible imaginary part, and you'll start getting two-photon absorption. So why do we call it two-photon absorption? Right. So here you see this effective absorption coefficient is proportional to intensity. Right. So in the usual linear absorption case, the absorption coefficient is a constant. Right. So it's independent of intensity. Right. So so in the propagation equation, right. So how this comes into the picture is right. So you have some wave propagating, and if you, in the material, if you see how the intensity varies with time, right? So for the linear case, basically you get this equation, right? Whose solution is the usual, the Beer-Lambert law, right? So exponential decay. So now in this case, I have an alpha effective. Right, and that alpha effective is also proportional to intensity. So this equation becomes so di by dz is proportional to I square. Right? So that's where the 2 is coming from. Right. So in the usual linear absorption case, yeah, basically I have the first order of intensity. So I'm absorbing one photon at a time. Right. So the usual linear absorption case, typically, if I denote some level diagram picture, usually it's denoted as you have some incoming photon, the atom absorbs that photon, transitions to some upper level, and then it can spontaneously decay. But the absorption is basically taking the atom from some lower level to higher level, right? So it's basically absorbing one photon. Right? An atom is absorbing one photon and going to a higher level. That's the linear absorption case, and that's where you get. So this is constant, and you get something just proportional to intensity, right? Because you're absorbing one photon at a time. Now you have I square. So basically, what that corresponds to is you're absorbing two photons simultaneously at the same time. Okay. So we can also get this equation starting from, let's say, if we start from the usual canonical propagation equation, right? So we have this propagation equation for the amplitude. Right? The usual canonical propagation equation for nonlinear optics, right? So in this case, again, we'll put this nonlinear polarization as a third order polarization at omega. Right, so this right, so the electric field here so if I write this, the electric field here as some E of omega times e to the minus I omega t plus complex conjugate, then that E of omega I can write as A times e to the I kz, right? And then I have a mod e square E here, so I get a mod e square A, and then I get a factor of e to the ikz. Right? So I get e to the ikz, e to the ikz, and e to the minus ikz from the conjugate. So I'll have one term left, which is e to the ikz, and that will actually get cancelled from this e to the minus ikz, which already is appearing in the canonical propagation equation. So basically, you can write dA by dz as right. And now we want to consider the case where, so if you consider pi3 as a real number, right, you can see that the solution to this would just be like A is some A naught times e to the I, some phase, right, and that phase goes as something which is proportional to intensity, so that would be the intensity dependent refractive index. But now, let's say pi3 is a complex number, has an imaginary part also, so this equation I can also take a conjugate. So here this I get here pi3 conjugate mod a square, and here I get a conjugate. Okay, so just take conjugate of this equation. And now I want to see how the intensity varies, PR by dz, right? So again, we did this for the Manley-Rowe relations, right? So we express again I as mod a square, which is a times a conjugate, and then di by dz will have a times dA conjugate by dz plus a conjugate times dA by dz. Right? So right, so if I want to write, so firstly, the intensity is that, right, and this is just A times A conjugate. So d I by dz right, and then I plug in the expressions for dA by dz and dA conjugate by dz. Okay, so you can see, so if you look at this first term, I have A times dA conjugate by dz, and dA conjugate by dz has mod A square A conjugate. So I get a mod A square A conjugate, and then multiplied by A, which means I get mod A to the fourth. Okay. Then the other term is just the complex conjugate of this. Right, so this I can write as like that. So now mod a to the fourth is just a real number, right? And I get chi3 minus chi3 conjugate. So I get, so this is the imaginary part, right? Complex number minus its conjugate, I'll be left with the imaginary part. So this will give me minus 2 times the imaginary part of chi3. Right, so I'll end up with something like, and again I express mod a to the 4. So here mod a square is proportional to intensity. So mod a 4 will be proportional to I square, right? So I get something which is proportional to I square, right? And again, if you look at that constant of proportionality, we'll get the same thing that we already derived. Okay. So this is a more direct way just to see directly from the canonical propagation equation. You get that the intensity propagates as something which is or decays at some constant times the square of the intensity. Right. So the beta here is proportional to the imaginary part of chi3. And the first couple of classes we sort of derived from a classical model the expressions for these susceptibilities, right? And then we saw like close to some resonance, the imaginary part will be appreciable, and as you go further away, then basically you can neglect the imaginary part and becomes purely real. So if you go into the quantum mechanical derivation of the nonlinear susceptibility, basically you'll see that turns out that this chi3, so if omega naught, like there is some band gap, let's say, which corresponds to some resonance frequency omega naught, then just from this level diagram you can see that two-photon absorption can only occur if 2 times h cross omega is more than Eg, right? So if, for example, omega is smaller, basically you just don't have enough energy to cross the band gap, right? So basically TP only occurs for frequencies which are more than half the resonance or band gap frequency. Right? And if you go through the rigorous quantum mechanical derivation, this automatically comes out in the chi3. Okay, which we didn't go through because that will take like another few lectures, which is yeah. So we didn't cover that in the course, but for example, chapter 3 of Boyd has some details on that. So if you are interested, you can see. Right, but yeah, the point is that again, so if you are working at a frequency which is smaller than half the band gap, then rigorously you can avoid two-photon absorption. Basically, this identically goes to 0 for omega less than omega. And so usually that is those are the frequency ranges at which usually we operate, right? Because this you can see is sort of like an additional loss, right? Because the intensity is just decaying in the material. So for example, silicon, right, has a band gap of about 1.1 electron volt. So this means that if your wavelength is smaller than 2.2 micron, then you get TP. Right, basically a single photon resonance wavelength. So if I write this as hc over lambda naught, that lambda naught corresponds to 1.1 micron, and so you need at least twice the wavelength or half the frequency to avoid TP. Right? So if your wavelength is less than 2.2 micron, then you get TP. Right? So this of course restricts my wavelength range. So if I want to avoid the 2-photon absorption loss, then I want to operate at wavelengths more than 2.2 micron. Right? If you look at diamond, the band gap is about 5.5, 5 times the band gap, which means I can work at 5 times smaller wavelength, right? So I can go up to about 440 nanometer. Right, so I can operate all the way up to 440, so I can almost cover the entire visible range also without getting 2-photon absorption if I use diamond. Silica, sort of the most widely used optical material, has an even larger band gap. So of course there's a trade-off, right? As I'm going to larger and larger band gap, we saw that the chi3, right, or for example the real part of chi3, which I'm interested in for nonlinear interaction, that also goes down. Right? So bigger band gap gives you bigger range of operation, but it also gives you smaller interaction. So if I look at glass, then the band gap is about 9 electron volt, and I can almost go down to like 200. It's about 250. I can go almost into the UV range, right? Right. So for the linear case, right? If we just have linear absorption, we know that the intensity decays exponentially with propagation, right? You can see that the form here is different, right? So for 2-photon absorption, I have di by dz equal to minus beta I square. So the intensity doesn't decay exponentially. But it's straightforward to solve this propagation equation, right? So if you have di by dz, it's a straightforward integration. So let's say I have some material here. This is z equal to 0, and the intensity at the input is in I naught. And then I want to see after propagating a distance z, what is the intensity I of z. So I integrate from 0 to z. Right, so here I get that. Right, so you can rearrange terms, and so Iz is basically I naught, 1 plus beta I naught z. Right. So the intensity is decaying sort of as 1 over the propagation length. Right. So the intensity falls off slower as compared to the linear case, where it falls off exponentially. Right. This is falling over as 1 over the propagation length. So if I have some medium of length L, right, and then so the output intensity is I of L. So if I define some transmission coefficient as I of L by I naught, the input intensity, that's 1 over 1 plus beta I naught L, right? So the transmission through some nonlinear medium depends on the length of the medium and also the input intensity. Okay, right? So, for example, if you contrast this with the linear case, right? In the linear case, so I have some I naught, I have some I of L. So I of L is just I naught times e to the minus alpha L. So the transmission coefficient is I of L divided by I naught, which is just e to the minus alpha L. So it doesn't depend on the input intensity, it just depends on the length. But for the two-photon absorption case, the transmission coefficient actually depends upon the input. That's why it's nonlinear. So if you plot the transmission coefficient versus input intensity, get some curve like this, right? So as I increase my input intensity, the relative transmission goes down, right? So this is 1 for I naught equal to 0. And then the point at which it falls to half, right? So that's I naught equal to 1 over beta L. Right, so it's basically saying that if you want to limit your losses, so if I want a high transmission through my material, then my intensity has to be lower than this 1 over beta. Right, I want to be here. So basically you want, if your beta is lower, you can have higher intensities transmitting through the material without loss, right? So this beta, for example, for silicon, so silicon here, the beta is about 1 centimeter per gigawatt. Right, so units are meter per watt, because basically beta times intensity. So intensity is watt per meter square, right? So when you multiply beta times I, you'll get 1 over meter, and then you multiply the length, that should be unitless. Right, so this is at the wavelength of 1.55 micron, which is used for optical telecommunications, and because that's so that's the wavelength range where optical fibers, silica optical fibers, have minimum loss, right? So basically all these transatlantic, transcontinental optical fibers are laid down, and basically the modern internet is set up because of that, and all the communication is happening at this wave, right? And so people want to make all optical devices using silicon now, which can be applied to optical telecommunications. But one bottleneck is basically that silicon has a fairly high two-photon absorption at this rate. So it has a very large N2 also, if you remember, like the real part, which gives the intensity dependent refractive index. And that's sort of the real part of Chi3 is what we can use for different interactions. So we'll study, for example, four-way mixing a little bit later. But it would be great if we can avoid these losses which are accompanying, right? So mostly two-photon absorption is a problem, I guess, but it can again also be utilized for certain things. So one application it can be utilized for again is microscopy, right? So if you go back to our discussion, basically we saw how if you have something which goes as some higher power of intensity, like a nonlinear dependence on the intensity, then we can get subdiffraction imaging, right? Basically, we can get we can image something which has a resolution which is smaller than the focal spot of my laser, because right, we saw that Gaussian profile, and if you raise it to some higher power, then the profile narrows. So similar thing can be done here, right? Because the absorption goes as I squared. So there is something called two-photon absorption based nonlinear microscopy also. So again, like I have my laser beam coming in, and then I focus it down into my sample, right? And typically, if I'm just looking at the usual fluorescence, then I'll get like some big, I'll get fluorescence from sort of this whole big region. So I'm looking along the depth now. Right, and the XY in the cross section, there will be a spot which is the diffraction limited spot that I can focus it to. But if you have, let's say you infuse your dye with some, infuse your sample with some dye which has, let's say, some large two-photon absorption at the wavelength you're illuminating, right? And then maybe, let's say, look for the fluorescence at twice the frequency. So you basically what the dye is doing is absorbing two photons, going up to some level, and then let's say fluorescing at something close to twice the frequency. So you look for that fluorescence, right? Then that will be proportional to I square, and you can. So this is a spot which is focusing down. I square will be. So I square will vary in a much faster fashion than the linear. So mostly you'll get fluorescence from here, near the spot. Okay. So basically you can avoid sort of the background around the region you're interested in, and you can get much better resolution. So that's used often. And a similar idea is two-photon lithography. So lithography is when you want to make some very small structures, right? So we make electronic components which are sub-micron and down to like tens of nanometers scale. We now also want to make optical waveguides which are, let's say, sub-micron. Right, and typically what is done is like you take some wafer, and then you coat. So this is some wafer, some, let's say, silicon wafer or whatever you have. Then you coat some resist. So there is a material called photoresist, which you coat onto this wafer, right? And then you illuminate using some pattern. Right. So again, let's say you can imagine like there's a lens here, and I'm focusing light and illuminating a very small region. And wherever we expose this resist to the light, it changes its chemical properties. For example, like dissolvability in some solvent, right? And so when you expose this and then you dissolve it in the solvent, basically the unexposed part goes away, and then only the exposed part remains. And then, like, you can do further processing like etching. So only this part will be etched, right? The part which has the resist on top will not be etched, and then you finally again remove this resist. So you end up with some waveguide-like structure on your silicon, right? So that's how photonic and electronic components are made, and so this process is called lithography. So if it, and more specifically photolithography, when this illuminating beam is an optical beam. Right, again you can see that what is the smallest waveguide I can make is probably the smallest focal spot I can get, which is the order of wavelengths in the linear case. Right, resists here which work on 2-photon absorption. Right, so basically, sorry.
So video is not visible.
Okay. Back now?
Yes, sir.
Yeah. Yeah. So in the usual linear photolithography case, right, the minimum size you can get is of the order of the wavelength, right? So let's say if I'm using some visible wavelength, I don't know, 600 nanometers, and that's the smallest size I can get. But if I want to make smaller, then I have to think of something more. So again, let's say if you have some resist which works on 2-photon absorption, right? So it only absorbs 2 photons. It doesn't do the linear absorption. So let's say it has some absorption levels which are more than the single photon energy, but lower than the 2-photon energy. And so it absorbs, it undergoes 2-photon absorption and undergoes this chemical change. Then again, this, if you look at this focal spot, if the focal spot is like this, so the intensity, let's say in some spatial direction is like that, then I square will have a narrower profile, right? So the feature that you will get will be smaller than the width. And not only in sort of the transverse direction, but also along the depth, right? So what I showed previously for microscopy holds for lithography also. So you can control the depth pretty well, right? So if I have a focal here, so usually if you do linear lithography, then basically this whole, it's difficult to control the height or the depth right around the focal spot. But if you do based on 2-photon absorption, then this region becomes smaller, right? Because this variation basically increases because we go square. So people can actually do very fancy 3D. You can make very fancy 3D structures using photolithography. So basically, you take a laser beam and you basically scan. It's like 3D printing. You scan it in whatever structure you want, and then basically dissolve away the resist. So I'll post some very nice papers on this. So, but you can really make very, very complicated structures with very good 3D resolution.
Sir, I want to ask one question.
Yeah.
So basically, 2-photon absorption is a shortcoming, like drawback, but we can use it for the application purpose.
Yeah. So as I said, so these are applications where we are utilizing 2-photon absorption, right? So there, the applications are we want to do something to some material, right? And we are not actually interested in what happens to the laser beam, right? So the laser beam undergoes 2-photon absorption, etc., and we are using it to process some other material or something. So we are interested in what happens to the material, right? So that's why it's a useful effect in that case. But if you are interested in how the optical beam is propagated, right? So let's say for optical communications, I'm sending some optical signal, optical pulses, and I want to receive it at the other end, right? So if any losses are occurring in between, then that's detrimental for me, right? So in that case, this would be bad, right? Similarly, if I'm doing some nonlinear interaction, I want to convert some optical wave from one particular frequency to another particular frequency. I want to do it efficiently, then I don't want losses in my optical fields, right? So if something like this is happening, it just adds to my loss.
Okay, sir.
Yeah. So. Okay, and then another very important application of 2-photon absorption is to measure optical pulses. Okay, so so-called autocorrelation or cross correlation of optical pulses. So yeah, in general, it can be used for measurement of optical pulses. So sometimes this is called autocorrelation. So autocorrelation is a mathematical term which just says that you take a signal and then you correlate it with itself. That's why it's called autocorrelation, right? Then there's also cross correlation where you take two different pulses, or in general two different signals, and then see what is the correlation between them, right? So in the context of optical pulses, so basically what is the idea? Let's say you have some pulse laser or some other source for optical pulses, so it's giving out pulses in time, right? So y-axis is power or intensity, x-axis is time, right? So, and these pulses can be quite short, right? So for ultra short lasers, these pulses can be so generally the range is about tens of femtoseconds for the shortest lasers to, let's say, could be tens of picoseconds for other lasers. So yeah, so the time range you're looking at is like 10 to the minus 15 to 10 to the minus 12, something, that kind of time scale, right? So the point is that it's very difficult to measure this directly, right? So if I take this laser and just put it onto a photodetector, the photodetector is not fast enough, so I'll get an electric current out here, right? And ideally what you want is that, okay, my optical power varies like this, my electric current should also vary like this, and then by measuring my electric current, I should be able to say what my pulse was. But for that, your photodetector needs to respond at these time scales, which basically is not possible. So the fastest photodetectors you can typically get are in the tens of gigahertz, or max maybe let's say 100 gigahertz bandwidth. So that corresponds to about, let's say, tens to 100 picoseconds. Okay, so that's the fastest response time that you can get from the most expensive photodetectors. Right, so there is no way you can resolve femtosecond timescales, for example. Right. So, for example, what will happen when you send this pulse train into my photodetector? My current actually doesn't look like that. It sort of looks like some average, so it just averages the power over whatever response time of the detector it is. So over the response time of the detector, there will be multiple pulses, and it just averages the power, and you get some quasi CWs. Right. So there is no way to from the photodetector current to say what my pulse shape is or what is the duration of the pulses, etc. Right. So then, how do I measure optical pulses? Right. So one way to utilize, or one way to do it is using two-photon absorption, and many of the commercial devices which are used for measuring optical pulses actually use this idea. Right. So what is the idea? So I have my input pulse here. Okay, so let's say it has some central frequency, omega, some duration, some pulse width tau p, which I want to measure. Right, so what I do is make some sort of Michelson interferometer. So split the pulse into two. and then retro-reflect both both the beams back, and then recombine. Okay, so I've drawn this beam splitter in the wrong direction. So this is called Mandel's disease. This drawing the beam splitter in the wrong direction. So there was a very famous optical scientist called Leonard Mandel, who's done some very fundamental work in coherence and optics, etc. And apparently, he used to draw this always on the wrong side. So it's called Mandel's disease. It's so fun, but that happens all the time. You want to draw it the right way, but it always happens. Draw the wrong way, but yeah. So you split the pulse into two and then recombine, right? And then you detect on what is known as a TPA detector. So your detector is now something which only gives a signal due to two-photon absorption. Okay, so in other words, the band gap of this material out of which you make the detector here is more than, so this h cross omega naught or Eg is more than h cross omega, but less than 2h cross omega. Right? So there won't be any signal just from the usual linear photodetection. Okay? But whatever signal you get will be because of two-photon. Okay, so and then you have one of these on movable arm, and then you have some delay on one of the arms. Right? And then basically what you do is you vary the delay here and then measure the current as a function of the delay. Current out of your photodetector is a function of delay. Right? And so when you do that, when you plot the photodetector current as a function of the delay, you will see that you sort of recreate the optical pulse. Right? Even though my photodetector is slow, right? This tau p is let's say sub picosecond. My photodetector only responds, let's say, a nanosecond or something, right? So how is this happening? Right? So what are you doing? You first fix this at one particular tau, right? At one particular delay between the two paths, and then you measure the current. Right? So what you are measuring is the average current for a particular delay. Right? So when there is a particular delay, what is happening? So from the two paths, you are getting two pulses which are slightly delayed from each other. Right? And basically the signal that you are getting here is proportional to the current. So if I call this some E of t, so the electric field profile, you're averaging E of t times E of t plus tau. Right? Or I of t plus tau. Right? Because the signal that you are getting is two-photon absorption, right? So it will be proportional to the two-photon coefficient times product of the intensities. Okay, so you'll get a signal which is proportional to the product. Basically,
So we are taking autocorrelation, right? Yeah.
Yeah. So if you have only one pulse coming in, it's called autocorrelation, right? So I just have one pulse source, and I want to measure what the shape of the pulse is. So I split that pulse into two and do this. So this is called autocorrelation. Right? So here you can see I'm correlating two things, but both of them are coming from the same thing, right? So it's autocorrelation. For cross correlation, you could have two different inputs, and you could see how much they overlap with each other. That could be cross correlation. Okay. But so you can see that basically the signal will only come from the portion where the pulses are overlapping, right? So for large delays, when the pulses are not overlapping at all, this quantity is 0, right? Because there's no overlap between the pulses. So basically, you're only getting signal where the pulse, where these two pulses overlap, right? And a maximum signal will be when both of them perfectly overlap, right? So as a function of the delay, as I vary this delay, I'll trace out this pulse, right? The maximum signal will be when these two path lengths are the same and the pulses overlap. That's when the peak will be. And as I increase this delay on both sides, then the pulses will start moving away from each other. The overlap will go down, and my signal will go down, right? So notice that now at each delay point, I'm actually measuring for a long time, right? I'm measuring multiple pulses and taking the average current out, right?
So video goes off. So
Yeah, hopefully it's that. Right, so the photo detector itself, the response time is very slow, right? So at each delay point, I'm sort of getting just a CW signal, right? I'm just getting some average current value. But the point is that value will change when I change this delay.
excuse me, sir.
Yeah.
Sir, this delay you are giving manually or something, like you have a device which like having the speed of like doing it for the nanosecond or something.
So this okay. So the point is okay. So you are asking how can we give? So the delay we want to give is within the pulse, right? So we want to give like femtosecond delays.
Okay,
How do we do that? But the point is that we take advantage of the fact that so how it's done is this mirror is mounted on some movable platform or post, and then we physically move that, right? And there's a micrometer here, and by turning that, I can move the physical position of this mirror, right? And the point is that, so how much do I need to move the mirror? So the distance is c times tau, right? So because c is so large, right, 3 times 10 to the 8. So let's say I take tau as 10 femtoseconds, so 10 to the minus 14 seconds. You can see, so the distance I need to move is about 3 times 10 to the minus 6 meter or 3 microns. Okay, so if you have a good micrometer stage here, you can, you can get very precision stages which have resolution, let's say of a micron, or some very good ones which have even smaller, right? So you can position this accurately up to a micron, right? So you can see that corresponds to time delays which are few femtoseconds.
Okay, sir.
Okay. Right. So I hope that's clear.
Yes, sir.
Right. So basically, the interferogram between the two signals depends on the delay. Right. So as I change the delay, my average photodetector output is changing. Whereas if I just directly detect it, then, for example, there's no way for me to recover these pulses, even if I delay or whatever. Right. I need something which goes as the product of, or something which goes as I square. Right? So you could have non-degenerate two-photon absorption also. So we just took one beam, but let's say if you have more than one beam, you could have two different frequencies. So you could have omega 1, one of the photons at omega 1, the other one at omega 2. And as long as omega 1 plus 2 is more than some band gap, then, right, so if this has intensity I1, this has intensity I2, then the absorption will go as beta TPA times I1, I2. Okay, so if I look at d I1 or d I2 by dz, that will go as beta times I1. So you could have non-degenerate. And you can try to see how you can get this from, let's say, starting from the canonical propagation equation. That might be a good exercise for you too. So consider two beams in the medium, omega 1, omega 2, and basically follow the same procedure that we did, but now consider both omega 1 and omega 2, and try to see if you can get this. Right? So you could have non-degenerate. So just to end this topic, so there is a figure of merit defined, which is basically the relative ratios of the real part and the imaginary part of chi3. So basically N2, which is the intensity dependent refractive index, divided by the two-photon absorption coefficient, and this with lambda is the wavelength of your operation or feed. And so this comes from the real part, and this comes from the imaginary part. So if you want to do some nonlinear optical interaction and right, you want to do some nonlinear interaction efficiently without having nonlinear losses, then you want this figure of merit to be high. You want large N2 but small beta. Okay. So basically the real part N2 gives you the phase shift, right? The nonlinear phase shift. So the nonlinear phase shift goes as K N2 I L, right, for some length L of propagation. Saw this last time. And we just saw that the transmission due to TPA follows this this behavior, right? So basically, you can see that so the N2 by lambda comes from here, and beta comes here, and then both of these terms you have I times L, right? So this ratio is sort of giving you how much phase shift, nonlinear phase shift you can get before your transmission goes down to some value, right? So for example, if this figure of merit is 1, that means what? You'll get a phase shift of 2 pi when the transmission goes down to half, right? So when beta IL is 1, then N2 over lambda IL is also 1, so the nonlinear phase shift is 2 pi, right? So before the intensity goes down to half, I'm able to get a nonlinear phase shift of 2 pi if the figure out merit is 1. So if the figure out merit is higher, you get higher phase shift for the same transmission. So for example, for silicon at the telecom wavelengths which are around 1.55 micron, this figure of merit is actually less than 1. Right, which is telling me that I have significant loss. You can do slightly better with these other materials called chalcogenides, right? So some examples are like selenides or with selenium. So they have larger N2 and smaller beta, and you can get F1 up to, you can increase it by an order of magnitude, say up to 10. Okay. Then another material which is used in sort of micro and nano photonics, nonlinear photonics, is silicon nitride. Okay. And for that, the band gap now becomes larger than twice this wavelength. So the figure of merit actually approaches infinity because beta is 0. Okay. But of course, N2 is only about 1/10 of silicon. Okay, so let's say for the same nonlinear phase shift, you need larger power here, but in some sense you can afford that larger power because there is no nonlinear loss. So again, it depends on a particular application, what kind of materials you want to choose. Okay.
Hello? What you have written at the bottom, where SI
Sorry?
at the that means what you have written at the bottom, silicon night
This is silicon
SIN.
nitride.
Or,
SIN,
okay. And this
silicon nitride.
N2 is 1 by silicon nitride,
One
and
tenth,
this is N2 by.
1/10,
Okay.
1/10 of silicon. So the real part of Chi3 is smaller, like about an order of magnitude smaller than for silicon, but the beta is much smaller. It's like almost 0. Whereas for silicon, you have appreciable beta, right? So the figure of merit for silicon is small, but silicon nitride is very large, even though the N2 is smaller. That's the point. Okay, so the next topic that we'll discuss is nonlinear birefringence. It is basically a consequence of the tensor nature of Chi3. Right. So basically, you could have. So typically, birefringence is the phenomenon of two different polarizations of my input wave experiencing different refractive indices. Right. So typically, that happens in anisotropic media. Right. So for anisotropic media, this linear susceptibility or the permittivity is a tensor, right? So for example, in the x direction, you could have a particular refractive index, but in the y direction, So this nx, which is the square root of so in anisotropic materials, for example, these are not equal, and so the x and y polarizations will have different refractive indices, right? And that gives basically birefringence, right? So, for example, if you launch some particular wave which has a polarization which is at some angle with the x and y axis, that polarization will actually rotate as the wave propagates through the medium, because the components have different phase shifts, right? So the phase difference between them keeps evolving and polarization rotates. That's the phenomenon of birefringence. Of course, you don't have birefringence in isotropic materials, right? Because by definition it's isotropic. But we'll see that if you have a nonlinearity, specifically chi3, then even in isotropic materials, you can get something like a birefringence. Okay. So the idea is, again, we have some material with chi3, okay, and we launch some input wave with a particular polarization. So in general, it could be some elliptical polarization. Okay, and you'll see at the output, due to the tensor nature of chi3, this axis of the ellipse has rotated. Okay, so this is the polarization ellipse. Of my input beam, and at the output that has rotated, even though the medium is isotropic. Right? So in the linear case, in an isotropic medium, the polarization will not change. Right? So again, so let's consider the input wave has some frequency omega, and it has different polarization components. Okay, so this is the field in the I cap direction, right? And I could have different components, so I could have x, y, or in general, let's say two components x and y. Okay, so any general, depending on these amplitudes for the x and y components, I could have any general polarization, right? So this E would be a complex number. So depending on its magnitude and phase of the two components x and y, I'll get some general elliptical polarization. Okay, so in the medium, I can write my third order polarization. Again, at frequency omega, because I want to just see how this wave at omega propagates. So I want to look at the nonlinear polarization also at that frequency. So if I look at the polarization which is induced in some direction I, again I can write using the tensor elements of chi3. Right, so I want to see the polarization in the medium which is induced in direction I. So the first index is I, and then the other three indices would be variable. And those three indices correspond to my fields. Right, and one of these will be conjugate, because again I want to see the polarization at omega, so I'll get omega plus omega minus omega. So one of them is conjugate. Right, so each of these j, k, l is let's say either x or y. right? So now if we consider an isotropic medium in the far off resonant regime or the Kleinman symmetry regime. Then if you recall, I can write any tensor element in terms of just three actually for now let's so let's not introduce the Kleinman symmetry now. So if I just consider an isotropic medium, then you know that there are only three independent elements, right? So by 1, 1, 2, 2. One, two, one, two. And 1, 2, 2, 1. Right? So recall that isotropic medium had only these three independent elements, and any tensor element we could write in terms of these three like that. Okay. So basically, if I put this chi3 ijkl into the expression for polarization here, you see that the only terms which appear are which have two of the indices the same, right? So I can write the nonlinear polarization okay, when I plug this in here, so the first term I have delta ij and delta kl. Okay, so basically ej, j is equal to I, so ej is ei, and k is equal to l. So I get a mod e k or mod e l square, however you want to write it. So that's here. Second term, I get delta ik and jl, right? So again, ik, so this ek is basically ei. And then I have jl, so j and l, that gives me mod e square again. Then for the third term, I have il and jk. So il, so this el conjugate now is ei, so ei conjugate. And then jk, so these two are equal now, so I get e square. Okay, so I hope this expression is clear. And now these first two, so now let's consider we are in, let's say, Kleinman symmetry. So far off resonant operation. Or actually maybe not yet, just after 1 step. So these two terms are the same, right? I just so I'm summing over k here. This is summing over L, but both are just summing over the indices, and I'm getting mod E square EI. So these two are actually the same, and I'm just changed the dummy index from k to L. Right? So these two are actually the same terms. So I can combine these two and write this as basically that, right? Okay. Okay, and now you can make the Kleinman symmetry approximation, assuming we are far off resonance. And in the Kleinman symmetry case, the permutation, we get full permutation symmetry of the indices, right? Which means this is equal to this is equal to this. Okay, so let's assume we are also in that far off resonance regime. So these elements are now equal. Right, so this I can write as 2 times chi 1122, and this I can write as just equal to chi 1122. Okay, and notice one more thing. So this is mod E square, sum over the directions of mod E square, which is basically the sum over the directions right. So this could be, let's say, x or y. This is just E dot E star. Right, so this is mod of Ex square plus mod of Ey square, which you can see is just E dot E star. Right, so if I write E as some x direction times Ex plus y direction times Ey, where Ex and Ey are complex numbers. Right, so this quantity is just mod Ex square plus mod Ey square, which is just E dot E star. Right. So this quantity, summation over the index L mod E square is E dot E star. And similarly the other one, so summation over the index E square, that is E dot E. Right, so this is Ex square plus Ey square, which is, you can see, is E dot E. Right, so basically we write this as E dot E star, and we write this as E dot E. Okay, so that means I can just write my nonlinear polarization as so the first term is 2 times chi 31122 E dot E star. And second term is so I can take the chi 31122 outside. second term is E dot E, and then EI conjugate. Okay. So this is the polarization induced in direction I. So the first term is proportional to EI, and then it has E dot E star. And then another term is proportional to EI conjugate, and it has E dot E. And so I can write this for any direction I, right? Which means I can just write the vector response right? So this holds true for any of the indexes x or y. So I can write the vector nonlinear polarization as so I get the vector E here. So Pi proportional to EI. So vector P proportional to vector E. And the second term is E conjugate. Okay. So basically I can write the third order response in terms of my vector electric field of my input. Okay. And so for an isotropic medium in the Kleinman symmetry limits, there is only one tensor element which is independent. And also we know that 3 times chi 1122 I can write as just to simplify it further, right? So recall chi 3 ijkl was each of the 3 terms delta ij, delta kl. So all 4 are the same. Then I get 3 times chi 1122. So I just replace 3 times chi 122 with chi 11. Okay, so you can see that you have one term which sort of goes as E, right? So this has what is known as same-handedness. Or same chirality as E, where this where E star has opposite handedness or chirality to my input bit, right? So what do I mean? So if I consider in terms of circular polarizations, right? Not xy but circular polarizations. So what are circular polarizations? So the unit vector for right-handed polarization sigma plus is basically the 2 components x and y with a phase difference 90 degrees, right? So that in the complex notation gives me x plus iy, right? And then the minus will be minus, right? So these are the right-handed circular and the left-handed circular polarization unit vectors, right? And so here you can see that if I have sigma plus, I have x plus iy, right? So this unit vector here, let's say I have sigma plus. If I take the conjugate, that becomes x minus iy, which becomes sigma minus. So that is what we mean by handedness here, right? So if E has some sigma plus component, then the polarization induced has a sigma plus component, the same handedness, plus it has a component which has the opposite handedness, which is sigma minus. Okay, and you can see that's where the birefringence is coming from, right? So it's I don't know, in your high school physics, you remember in a sugar solution, if you pass some linearly polarized light, then after this passing through the sugar solution, the polarization rotates, right? And that's because the sugar molecules are chiral, right? Which means they have some handedness. So the refractive index seen by the right and left circular polarizations are different. So you can write the linear polarization as a superposition of right-handed and left-handed, and then both of them acquire different phase shifts, and then the output when you recombine, it's at an angle. So you can see something similar is going on here, right? My nonlinear polarization has a contribution from the same handedness and also another one from the opposite handedness, and the magnitudes are not the same. Right? If the magnitudes were the same, then it will be something like, again, which is not something which that will again result in something which is not birefringent. But because the magnitudes here are not equal, this will give rise to something like birefringence. Okay, so then basically we write the input wave in the circular polarization basis. So I write it like that. Okay, and so magnitudes of E plus and E minus will give me what is the ellipticity of this, right? So for example, if E plus and E minus, the magnitudes are equal, that means this will be linear polarization, right? Equal superposition of circular. But if the magnitudes are not equal, then it will be some elliptical polarization, and then if one of them is zero, then it will be circular. Right? So those are the limits. Right. So if we write my wave like this, then we can compute these quantities E dot E and E dot E star. So E dot E star, let's see first. So that will be so what is sigma plus conjugate? That's just sigma minus, right? So this is the sigma minus, and sigma minus conjugate is just sigma plus, right? So now when we take the dot product, um, maybe that's not probably the way to do it right now, because so thing to keep in mind is that, so in the usual Cartesian basis, right, if I write it x and y direction, we know that they are orthogonal in the sense that x dot y is 0, right? But the unit vectors sigma plus and sigma minus are actually not orthogonal. So if you do sigma plus dotted with sigma minus, you actually get 1. Okay? and it's actually the relationship is a bit weird. If you do sigma plus dotted with sigma plus itself, then you get 0. Okay, or minus with itself, you get 0. But when you take the dot products of the, I mean, you can just write sigma plus as x plus iy, and then sigma minus as x minus iy. You will see that the unit vectors are related sort of in the opposite way that you would expect. Sort of. So this is not an orthonormal basis, basically, is the point, right? So maybe let's just keep it as, or maybe after that. So now this is sigma minus, and this is sigma plus, right? So the terms that will remain here are the cross terms, right? So sigma plus dotted with sigma minus, that is 1. So e plus conjugate will give me mod e plus square, right? But the sigma minus dotted with sigma minus gives me 0. So I don't have that term. Similarly, I get, so here I have sigma plus, so I get the sigma minus dotted with sigma plus, so that will be e minus conjugate. So that will give me e mod e minus square. Right? I hope that's clear. Right? And similarly, you can compute e dot e. Right? So for e dot e, I have the same this term coming again here, and so again I'll get sigma plus dotted with sigma minus. So I'll get e plus e minus, and the second term will also be e plus e minus, right? The sigma minus dotted with sigma plus. So this will be twice of e plus e minus. E dot e. Okay, so when I write my input wave in the circular polarization basis, I can compute e dot e star like that and e dot e. So hope that's clear. If not, let me know. Okay, so the next step is just so this polarization expression, we've computed what is e dot e star and e dot e. So you can just plug in those values. So the third order polarization here becomes so e dot e star is mod e plus square plus mod e minus square. And then E I write it as E plus sigma plus E minus sigma minus. Right? And then the second term is 2 times E plus E minus. E plus, so I have E conjugate here, so sigma plus becomes sigma minus, and then this is conjugate. This becomes sigma plus. Okay. And now we just collect the terms corresponding to sigma plus and sigma minus together. So basically, we want to see how each handedness responds, right? So we want to collect the sigma plus terms together and the sigma minus terms together. We'll rewrite this as right. So I can write this. Okay. So for sigma plus, I get mod of e plus square plus 2 times mod of e minus square times e plus sigma plus, and for the sigma minus, I get e minus mod square plus 2 times e plus mod square. Right. So these two terms are different. If let's say e plus and e minus are not the same, then these two terms are in general different. Right. So you can see this is how my input wave was e plus sigma plus e minus sigma minus. So the sigma plus component, right, that's coming here with this coefficient. So this should be familiar, right? So this is chi3 times some mod e square times my field. So this looks like self-phase modulation, intensity dependent refractive index, right? Similarly, this term, but it's just that the magnitude of these two terms in general are not equal, right? So in some sense, you can or you can deduce that the phase shifts or the nonlinear phase shift due to self-phase modulation is different for the sigma plus and sigma minus components, right? Which is basically birefringence, right? The phase shift for the two circular components are not the same. Right. So if I write this as a response for the sigma plus component and response for the sigma minus component, right? So I'm just writing the two parts separately. So then this plus minus is this last line visible?
Please you repeat that line, last line.
right? So I basically collected sigma plus and sigma minus terms, and then the coefficient of each is like that. So you can see if E plus and E minus are not the same, then P plus and P minus are not the same. Right? So, yeah, the point is the sigma plus and sigma minus components will acquire different nonlinear phase shift if E plus is not equal to E minus. Right? So E plus equal to E minus, if you see from here, is basically linear polarization. Right? If the two circular components have equal magnitudes, or if mod A plus equal to mod E minus, this is linear polarization.
Both of us also.
Sorry?
The video is not visible, sir.
Okay, hopefully it's back.
Yes, sir.
Yeah. So if mod E plus is equal to mod E minus, it's a linear polarization. You can check yourself, right? You can take this as IY. If one of these is zero, either E plus or E minus, then it's circular polarization. You know. In the other general case, when these two are finite but not equal, then it's some elliptical polarization, right? So what is it saying here? If you have input linear polarization, when mod E plus and mod E minus, then P plus is equal to P minus, right? And then you can write the whole thing as again the usual self-phase modulation case, right? Chi3 times mod E squared times E. So that will just give me some phase shift. That won't give me any polarization rotation. But if these two magnitudes are not equal and my input is some elliptical polarization, then you see that the two components actually acquire different phase shifts. Right? And so you can see that I can write like the sort of mod E square as the intensity in the sigma plus component, and mod E minus square as the intensity in the sigma minus component, right? So each of these terms will give me a phase shift or nonlinear phase shift. So the nonlinear phase shift for the two components plus sigma plus and sigma minus, right? I can write it as okay, where N2, if you recall, depends on chi3, right? So I've just written, so this we know is omega over c N2 I z, right? So instead of the usual just I for one, if you have just one beam, you get the I here. I have two components of I, right? I plus and I minus, which is the, so basically I'm writing right, 2 n naught epsilon naught c mod E plus square as I plus and minus is minus. Okay. Right, so I hope this is clear. I can write a nonlinear phase shift, so I can define the corresponding N2 from this and write the nonlinear phase shift like that. So for the plus and minus. So if you can see, if I plus is not equal to I minus, then phi plus is not equal to phi minus. Right? If it is equal, then phi plus is equal to phi minus, and the whole both components acquire the same phase shift, and my output polarization remains the same. But if not, then yeah, the polarization actually rotates. So at the output, so after some propagation distance z, my output is now, so E plus was my input, and now it acquires a phase which is phi plus nonlinear. That's the sigma plus component. Then the sigma minus acquires phase shift phi minus. Right, so that's my total field at the output or after distance z. Right, so here I can just take out a common phase, which is the average of the two. So phi plus phi minus by 2. Then I have here a difference, phase difference between the two. Okay. And so this phi plus nonlinear minus phi minus nonlinear, that's the difference in the phase shifts of the two polarizations, right? So let me call that theta. For phi plus minus phi minus by 2, let me call that theta. And this is some average phi bar, phi plus phi minus by 2. So I can write this as, so this is some global phase which is irrelevant. And then here this is E plus e to the I theta, sigma plus, E minus e to the minus I theta, sigma minus. Okay, so this should be familiar, right? So I am adding a phase difference theta and minus theta to the two. So what it will be is basically a rotation by angle theta of my, let's say, major axis of the ellipse. Right? So to see that explicitly, what you can do is sort of write this as E plus sigma plus prime. Right, so I define the primes as the original circular polarizations multiplied by this phase, right? And if you want to write this as some new like a circular polarization in some new axes, so x prime plus minus I y prime, and the original ones were x and y. You can relate x prime and y prime to x and y. Okay, and you'll basically get that. So x prime is x cosine theta minus y sine theta, and y prime is x sine theta plus y cos theta. So basically, what you're doing is, let's say, rotating the coordinate axes by theta, or equivalently for the same coordinate axis, rotating the ellipse by theta. And this angle of rotation, this theta, right, is phi plus minus phi minus by 2. And from here, you can get this angle of rotation. So theta is depends on the propagation distance or the length of the medium. Right. So the amount of rotation depends on the difference in the intensities between the two circular components. So if they were equal, which means a linear polarization, then there is no rotation. But in general, if you have general elliptical polarization with these two unequal components, then there is a rotation. Right? And yeah, so it depends on intensity and goes linearly with them. Okay, so this is called nonlinear ellipse rotation. Right, and it's basically a manifestation of some kind of birefringence that you're inducing in the medium due to the nonlinearity, right? Even though the medium is isotropic. Right? See. So maybe I'll just give sort of one application for this kind of effect quickly. We talked about sort of self-focusing and laser mode locking previously, right? So that was called Kerr lens mode locking. This kind of nonlinear polarization rotation is also used.
Excuse me, sir. Video.
Sorry? Video?
Board is not visible to us, sir.
Okay. Yeah, so this kind of thing also, you can see that it's an intensity dependent effect, right? So the amount of rotation depends on the relative intensity or the difference in the intensity between the two circular components, right? So for example, what you can do is, so let's say I have some input linear polarization. Right, I put some quarter wave plate at some angle theta, let's say, to introduce or to make this polarization elliptical. Right, and now let's say I have a nonlinear medium and I get some ellipse rotation here. So right, and then I put the another quarter wave plate at the same angle. Okay, so if there was no rotation and I get the same polarization here, then this quarter wave plate will recover my initial linear polarization. So before that, let's say I have a polarization beam splitter or something, and let's say the linear polarization, the original linear vertical polarization goes through, right? So now if the intensity is high enough, then you'll have some rotation and then you'll get a component after the wave plate here in the other orthogonal polarization, right? Because basically, because the ellipse has rotated, when you put the second quarter wave plate at the same angle, it does not recover to linear, but like some small ellipticity here, right? Which means that there's orthogonal component there. Okay, so for example, what you can again use this for is like mode locking in a laser cavity. So let's say I have some mirror here and I recycle this beam and send it back here. So I guess I need another half wave plate or something to rotate this polarization back to this. Right? So, and let's say here you have some laser gain medium or something. Right? So again, what this will do is force the cavity to operate in a high intensity or mode locked region. Right? So what are you doing? So if the intensity is low, there is no ellipse rotation. Right? This sort of behaves like a linear medium. So there's no ellipse rotation, and after this, you recover your linear polarization back, and it just passes through. Right? So it just leaks out of the cavity. So if the intensity is low, it leaks out of the cavity. So the cavity loss is high for low intensity. But let's say if the intensity is high enough, then this ellipse rotates, right? And then you get a significant portion going back into the cavity and recycle, right? So this will force the cavity to resonate in a high intensity or mode locked mode, similar to like the Kerr lens mode locking we're talking about. So for example, this kind of idea is used.
Sir, if you don't mind, can you please repeat it again, sir?
Yeah, so just recall the concept that we studied, right? So that was, we have some input wave. So let's say we start with a linear polarized input wave, right? And then we put some quarter wave plate at some angle to make it elliptical. And now we have a nonlinear medium. So if the intensity of the beam is high enough, then we'll get that polarization rotation, right? So this angle of the ellipse will rotate depending on, again, the intensity here. And then again, if you have another quarter wave plate at the same angle here to recover, so let's say if there was no rotation, then after the second quarter wave plate, the ellipse comes back to the linear polarization that was at input, right? So in the linear case, nothing happens. Linear becomes elliptical, then elliptical becomes linear again, and then this vertical linear polarization goes straight through this TBS. Right? But now let's say the intensity is higher. If the intensity is higher, then this ellipse will have some rotation because of the nonlinearity. So when it rotates, now the second quarter wave plate is not recovering the polarization back to linear, right? Because this was set for the ellipse at that angle, but now it's rotated. So the polarization after the second quarter wave plate will not be linear. It will have, let's say, some small ellipticity to it. Equivalently, there will be the orthogonal polarization component, right? So you'll get some reflection here, right? And now, if I set this up inside a laser gain medium, right? So I have a laser cavity and gain medium, and my light is coming like this, right? If I feed this back into the laser cavity, then it's forcing the cavity. So the laser will lace in the mode where the loss is the lowest, right? So which mode has the lowest loss? When the intensity is high, right? So it's similar concept to the Kerr lens mode rotting. We had an aperture. When the intensity was high, it self-focused and went through the aperture. So the high intensity had lower loss. Similarly here, the higher intensity will have rotation, which means it will have a reflection back into the cavity. But if the intensity is low, there is no rotation. It goes straight through and goes out of the cavity. Okay, and all this thing could just like be, let's say, some length of optical fiber. Right, so the optical fiber has its own nonlinearity. Okay, you could have like polarization controllers, or you could have like TM fibers where you could do this polarization rotation also. So, or at least the nonlinear medium, easily you can just replace by an optical fiber. And so, for example, there are fiber lasers where everything is a fiber. So this gain medium is also some erbium loop fiber or something. Right? So everything is just fiber component integrated, and you get a mode lock laser out. So pulses ultra short pulses. Okay. So that's one of the concepts used
So
in
in this
yeah.
experiment, you have ignored the dispersion terms and all. There is no dispersion, nothing.
Yeah. So if once you have like short pulses propagating and then you have fibers, then you have to start worrying about dispersion, compensation, etc. But yeah, for now we haven't studied about dispersion. Let's assume. I mean, there is ways to compensate dispersion also, uh, both in free space and in fibers. But that you can, let's say, do separate. Like you could have like dispersion compensation. Right, you could have separate. So, for example, in free space, you have these prism pairs and grating pairs, which can do that. In fibers, you have fibers of different dispersion values, positive and negative, which you can use to compensate. So that you can do separately. So you can compensate for the spreading of the pulse that you're talking about. Right? So, but just to get the laser to mode lock, um, like this can be used, for example.
Okay, sir. Okay. Thank you, sir.
Okay, so basically, yeah, which fundamentally is quite an interesting effect, right? You're starting from an isotropic medium, but somehow you're getting polarization dependent effects. So that is the, I guess, utility of this. Okay. Any other questions?
Sir, I have question regarding the two-photon absorption effect.
Yeah.
Suppose I'm not considering TPA. If I want to just in this photo detection, like I want to detect picosecond or femtosecond pulse, instead
Mhm.
of using TPA effect application, if I use it through SBS, can I can it be possible to do it by SBS?
SBS. So SBS, I mean, we'll study about Brillouin scattering later in the course, but so Brillouin scattering, like you can define some Brillouin gain, and typically that scales with the intensity. Okay, so if you have a pulse, like that will give you some Brillouin scattered light, and the higher the intensity of the pulse, the higher the scattering, and you
So
just scale as the intensity. So I don't know. So if you have two pulses, like it will just depend on the sum of the intensities, not the product. I mean, I don't know exactly what you're thinking of, but if you're thinking of this pulse as acting as the pump to generate some Brillouin scattered light, and then you want to do this splitting and recombining, and I don't think it will work.
but because there also the pulse width is line width is very narrow, sir. So can I think
Uh, Pulse width is, I don't know what you're talking about. I mean, the Brillouin gain line width is very narrow, right? If you have broad pulses, or sorry, if you have short pulses in time, that means you have a broad spectrum, right?
so sorry,
And
sir,
then the Brillouin, sorry,
board is not visible to us.
yeah, no. So the point is, you actually want a broadband response, right? So if you are looking at ultra short pulses, they have a very broad spectrum, right? And whatever nonlinear interaction you're using, better have the bandwidth, or at least the bandwidth of the pulse, right? So that way, actually, Brillouin is very narrow, right? So typically, the Brillouin gain line width is it's a megahertz or something, right? But if you take femtosecond or picosecond pulses, the bandwidth is terahertz, right?
Okay, sir. Okay, sir.
So yeah. So there are some autocorrelators or pulse measurement equipment that you can make out of, for example, second harmonic generation. Okay, so instead of TPA, what you do is when you recombine these two pulses, you combine them on a second order nonlinear medium, right? And then you detect the sum of the second harmonic, right? And then the second harmonic again goes as I square, right? So again, the signal will be maximum when the pulse are overlapped, and the signal will go down as you move the delay. So yeah, so you have autocorrelators based on second harmonic generation or two-photon absorption. Those are mainly two types of pulse measurement devices or autocorrelators or cross correlators that you get. Right, and the point is that typically, so this TPA and SHG are broadband effects, right?
Okay.
So basically, this omega to omega giving 2 omega. This could be really broadband. So I could have some different omega prime and omega prime giving 2 omega prime. So as long as, I don't know, your band gap is somewhere far away, all of this happens equally efficiently. Right, so if you have a broad pulse, so in the frequency domain, let's say you have different frequencies, right, omega prime, then all of them are converted. Similarly for TPA, as long as the frequencies add up to twice the band gap, you could have like different frequencies, omega, omega prime, omega double prime. Right, so for ultra short pulse measurement, you need some effect which is broadband. In that sense, Brillouin scattering would be actually not used. Yeah.
Okay, sir. Sir, can I ask one question not including in this subject? Just one single question, sir.
Yeah, go ahead.
Sir, how much will be there a difference in double sideband modulation and single side modulation at the PD if you modulate is using MZI? My 3 dB or 6 dB, sir?
I don't know. I guess you can find out from. So basically, the signal that you will get will be proportional to mod E square, right?
Yes, sir.
So I don't know. Depending on what, you can take some carrier amplitude and some sideband amplitude. Right. So in one case, you will have both these sidebands. In one case, you will have only one. So I guess the beat signal goes as twice, right? So I don't know. I guess the current will be doubled, which means the electrical power will be 4 times because it's I square, right? So it depends
Okay.
on if you're looking at the electrical current or the electrical power.
Sir,
One will be,
actually, it's electrical current, sir. Basically, it's a E square only.
yeah. So then current I think will be 3 dB, right? Because you just get twice the signal. Think.
Okay. Okay, sir.
Yeah.
Thank you so much, sir.